Hello, we are Group 41, and today we'll be presenting our project, the Aether Sensor Network.
My name is Paul Wood. The other members of our team are Ian Wallace, Park Benjamin, and Randy Alvarez. Here shows the Aether node inside our 3D printed enclosure. The battery connects at the top of the enclosure, with USB and antenna connections on the left and right respectively. The BME688 and ZMod4510 are ICs on the board, and the SPS30 is mounted below the PCB, with slits to provide airflow for its fan and laser. This is our outdoor gateway, which is a Raspberry Pi with a Rack 2445 LoRaWAN Pi hat, providing 27 dBm output power, and receiving sensitivity down to negative 139 dBm. It's mounted inside a project box, with a GPS mounted internally and an SMA connector to provide an antenna connection outside the enclosure.
Here you see the DC barrel jack input where the solar panel gets connected to. From here it goes to a filtering capacitor that helps stabilize the voltage coming from the solar panel. Connected to it is a reverse diode that prevents any voltage leakage coming from the capacitor. This connection then goes to the charge controller. We also have a USB-C input that gets directly connected to the charge controller. This USB-C also goes through an ESD protection diode circuit that helps prevent against any electrostatic discharge. From there, it goes to a USB to UART IC that helps us communicate via USB to the microcontroller. These status LEDs here are connected to the MCP as well as the LoRa microcontroller and help us read the status of the battery charging state. This thermistor is also connected to the MCP, and for testing purposes we have a 10K ohm resistor connected to it, but when the thermistor gets connected, it'll help us read the temperature of the battery and ensure that the battery doesn't get charged in unsafe conditions, for example, when the battery gets too hot. This is the LDO that outputs the constant 3.3 voltage. This LDO powers the BME sensor, the LoRa, as well as the ZMod sensor. This boost converter gets powered by the battery and outputs 5 volts to power the PM sensor. It also comes equipped with a shutdown pin that gets connected to the LoRa so it can be shut down to activate a low power mode. This reset button is for the LoRa microcontroller. Here you can see the antenna that's surrounded by ground vias to preserve signal integrity in the RF signal. This SWD programming header is to program the microcontroller.
First, we'll demonstrate a basic indoor test of the Aether node to show the ability of the node to function indoors. The Aether node is currently mounted on the 3rd floor stairwell of the engineering building. It is successfully transmitting data to the members of our team located on the bottom floor, near where the gateway is connected. The web application shows various data types or layers to overlay on the map, and a slider to show up to a week's worth of data. We have layers for different types of AQI, pollutants, humidity, temperature, and pressure. However, for this demo, we only had data from the past few hours. The circles on the map show different locations that readings were taken at, along with the corresponding values. You can click on the devices to view more details and graphs for real-time and historical data.
Next, we will showcase how we tested the outdoor range of the Aether node. For this test, we had the gateway mounted in front of Milliken Hall, while the Aether node was located across campus near the flagpoles of Memory Mall. As you can see, we are receiving data from the Aether node, and it is showing up on our website. Just to get an idea of how far away we were, we recorded this footage showing us traveling from the gateway to the Aether node. Before performing this range test, we only had a vague idea of how far the transmission range was. However, as you can tell by how much we sped up this footage, we were quite satisfied with the results. As it turns out, we were able to transmit a distance of approximately 576 meters. This slide shows the straight line distance between the gateway and the Aether node. The Aether node was able to transmit through multiple buildings and objects, all while the gateway antenna was located only 6 feet above the ground. We will now go over all 3 of our demonstratable requirements before demonstrating each of them individually. Our first demonstratable requirement is to be able to calculate the AQI within 25% of the EPA's reported value. Next, our second requirement is that our device shall have an average power draw of less than 100 milliwatts. Finally, our third requirement is that our device shall be able to automatically take a sensor reading from each sensor every 15 minutes.
For our first demonstratable requirement, we will be showing that the Aether node is able to calculate the AQI within a 25% margin. In this video, we have the Aether node placed outdoors taking sensor readings. The gateway is placed nearby on an apartment balcony. On the left side of the laptop screen, we have the Aether website pulled up showing that we are getting an AQI reading of 9. On the right side of the screen, we have the EPA's Air Now website showing an AQI reading of 16. This is within the 25% margin, given that the AQI is always an integer and we truncate it, thus meeting our requirement.
In order for the Aether node to be deployed as maintenance-free as possible, we made our second demonstratable requirement that the Aether node must draw a maximum average power of 100 milliwatts. Measuring AQI requires a particulate matter sensor, which requires a laser to measure various particle sizes and a fan to circulate the air to get fresh samples. We designed our firmware to operate in ARM's low power states, stop one, and periodically wake up to perform measurements. As you can see here, to measure the power consumed, we perform high side current sensing by connecting a 1 ohm current sense resistor between the positive terminal of the battery to the positive input of the battery power port. Beforehand, we verified the experimental resistance in order to get accurate calculations. We also had the gateway online to demonstrate that the microcontroller is still able to send packets. For measuring the power consumption of the Aether node, we wanted to match the parameters used when deploying Aether. For this, we take 4 readings an hour. In each hour, the SPS30 is powered on for 3 minutes, and the other sensors are sampling over a period of 30 seconds. The SPS30 requires a minimum of 30 seconds to warm up, then additional time between each reading in order to get accurate results as specified by the datasheet. The ZMod 4510 also requires special attention, and during its 30 seconds that it's turned on, it's sampling at a rate of approximately 2 seconds. We performed 2 tests, one with and one without the solar panel. The data is recorded using the analog discovery and is exported for further analysis. As shown, we recorded data for approximately 20 minutes to get data for one whole period. Ignoring the initial inrush current, our average current comes out to be 18.7 milliamps. The maximum current draw is almost 200 milliamps, which is from when the SPS30 is powered and data is being transmitted over LoRaWAN. Our sleep current was measured to be approximately 1 milliamp, with the minimum ever recorded as 832 microamps. With the average battery voltage of 3.9 volts, we recorded an average of 37 milliwatts of power over a single period, fulfilling our requirements. Since we have the solar panel to account for the power requirements of the sensors, we wanted to test what our net power consumption would be with it. We performed the same experiment as performed indoors, but outside on a clear day with the solar panel. We were able to record a net charging of the battery, approximately 183 milliamps, or 730 milliwatts. Also, we don't notice the same spikes when the data is transmitted over LoRaWAN and square waves when the SPS30 is powered, due to the solar panel supplying additional power under the increased load, while still charging the battery at the same rate.
For our third demonstratable requirement, we will be showing that the Aether node can take a sensor reading every 30 seconds. As you can see, we have a terminal pulled up showing the data being received from a serial USB connection to the Aether node. The first batch of sensor readings have a timestamp of 15 minutes and 3 seconds. Once we wait 30 seconds, we can see that the second batch of sensor readings have a timestamp of 15 minutes and 33 seconds. It should be noted that we set the time between sensor readings to be 30 seconds for demonstration purposes. This delay is easily configurable in our firmware, and it would be set to 15 minutes in a real use case.
We will now go over the results of our demo. For the first requirement, the AQI calculated by our device was 25% below the EPA's reported value, which satisfies this requirement. For the second requirement, our measured average power draw was 73.4 milliwatts, which was within range of the requirement. And finally, for the third requirement, we showed that we were able to configure the sensor reading to any value, thus satisfying this requirement.